a workflow for offline model-free robotic reinforcement learning, and present some real-world experiments to validate our approach. Standard online reinforcement learning typically maintains a tight loop between interacting with the environment to collect on-policy rollouts and training neural network controllers. This requirement for active data collection from scratch each time a robot is trained makes it extremely prohibitive to train effective and generalizing policies, especially in scenarios where data collection is expensive or unsafe. On the contrary, offline reinforcement learning methods allow us to utilize a big dataset which is already collected from previous experiments or past interaction, and it's only collected once, to train a policy that can generalize and be deployed in various new scenarios. This allows us to leverage and obtain not only better generalization, but also has no requirement for expensive or unsafe active data collection, which is completely the bottleneck with standard online reinforcement learning in real open world settings. So, natural next question to ask is if offline RL methods which are already out there can be applied to real robotics problems. To understand the answer to this question, let's revisit the same question in the context of more standard machine learning algorithms. So in order to apply machine learning algorithms to real-world problems, I would argue that we require two main ingredients. First of all, we require an algorithm to use. For example, we would typically use cross-entropy minimization using stochastic gradient descent. And second, we need a set of workflow or guidelines which can be used by a practitioner to make a lot of design decisions, such as when to increase or decrease network size, when to add regularization, when to change certain hyperparameters. Using a combination of both of these factors, a practitioner can effectively apply machine learning algorithms to their problems. For example, they could measure some sort of a validation loss by keeping a held out validation subset of the data, perform some sort of early stopping if they see that the validation loss starts increasing even though the train loss is decreasing. They could increase the network size if the training loss is still high, and add all sorts of regularization using these metrics. In this paper, we ask if we can devise a similar workflow for offline reinforcement learning. Tuning offline reinforcement learning methods in a purely offline manner without access to any online interaction to evaluate any policy checkpoint found during training is extremely challenging and has been noted by several prior works. To devise a completely offline workflow for offline reinforcement learning, we want to come up with a set of metrics that practitioners can track and a set of guidelines that practitioners can utilize to tune their methods on the basis of these metrics. To devise such a workflow, we utilize conservative Q learning or CQL as our base algorithm. CQL essentially trains a Q function, not only using standard temporal difference error objective, but also using an additional regularizer that aims to minimize erroneously high Q values and maximizes the dataset Q values. Our goals here are to characterize scenarios in which CQL overfits and underfits, and devise offline metrics that can indicate this behavior of CQL. Second, we want to be able to provide a criterion for deciding which policy checkpoint should actually be deployed in the real world, and this we'll refer to as early stopping or policy selection. And finally, we also want to provide some guidance to the practitioner as to how they should tune their regularization or network capacity decisions. Our proposed workflow for CQL runs the base CQL algorithm on the offline dataset and then characterizes its behavior into two cases, overfitting or underfitting. In order to do so, it tracks the Q values on the dataset to measure overfitting. For example, if the learned Q values show a first of all increasing and then decreasing trend as a function of the number of training gradient steps, then we characterize this scenario as overfitting. In such a scenario, we would suggest the practitioner to do early stopping at the point where the Q values attain their maximal value. Similarly, a large value of the training temporal difference error or the value of the regularizer that CQL adds indicates that the method is underfitting. In the case when the method is underfitting, we suggest that the practitioner increases the network capacity or adds some sort of capacity increasing regularization to improve performance. Whereas in the scenario where the CQL is overfitting, we suggest that the practitioner adds a capacity decreasing regularizer to improve performance. We now empirically evaluate our approach on 3 real robotic domains, 2 of which require training a Sawyer robot to place a lid on a pot and open a drawer, both in the presence of visually diverse distractor objects, and the third domain is a pick-and-place task on the Widow X250 robot. We'll now show how to tune CQL on these domains using our proposed workflow without access to any online tuning. In the first scenario with the soil manipulation tasks, we follow our workflow and plot the learned Q values and the training temporal difference error for CQL shown in dashed lines, as well as CQL with an increased network capacity shown in solid lines. We observe that the Q values do not increase and then decrease during training, which indicates the absence of overfitting, and the training temporal difference error is extremely large and increases during training for the base CQL algorithm, which indicates underfitting. The training error is reduced when a larger ResNet architecture, which is shown in the solid lines, is used, and this indicates that the larger network addresses underfitting as per our proposed workflow. Note that this decision was made completely offline without access to any online tuning. We now demonstrate the effectiveness of our workflow on these tasks by actually evaluating the policy checkpoints found by the base CQL algorithm and our tuned version of the CQL algorithm, which utilizes a larger network on these two Sawyer tasks. As you can see, the base CQL algorithm is unable to solve any of the tasks and attains 0 successes out of 12 trials with different objects for each of the two tasks. On the other hand, our tuned CQL algorithm is able to perform both of these tasks with a wide variety of different distractor objects, as you can see on the slide, and attains a success rate of 9 out of 12 and 8 out of 12 respectively on the pot and the drawer tasks. This indicates the efficacy of our workflow in detecting and addressing underfitting with CQL. The goal of our next task is to tune CQL for a real WidowX pick and place task, where the aim is to pick an object from different locations in the scene and place it in the pink tray. The dataset in this case is collected using a noisy scripted policy with an average success rate of 35%. And the dataset only consists of 200 trajectories. When we run offline CQL on this domain, we find that the Q values exhibit an increasing and then decreasing trend as shown in the blue line on the plot that you see on the slide. And this is indicative of overfitting as per our proposed workflow. Our workflow would here suggest deploying the policy near the peak in the Q value in the real world, and this is indicated by the vertical green line. Secondly, to address this overfitting issue, our workflow would suggest utilizing a capacity decreasing regularizer, and in this case we utilize a variational information bottleneck regularizer to regularize the internal representations of the learned Q function. As shown in the plot on the right, this regularizer gives rise to much more stable Q values, which you can see as the brown line in the figure, as compared to the blue line, which corresponds to the original base CQL Q values, which indicates that this regularizer is effective in preventing overfitting. Next, we evaluate the efficacy of our workflow both in terms of the policy selection criteria as well as the information bottleneck regularizer on this domain by actually evaluating the policy found by these various algorithms. First of all, we find that the baseline CQL algorithm obtains only a 3 out of 9 success rate and generally fails to solve the task from various object positions, especially the ones that are farther away from the default position of the gripper or the starting position of the gripper of the WidowX robot. When our policy selection rule, which picks the policy corresponding to the peak and Q values, is utilized, the success rate of CQL on this task increases to 7 out of 9, which is more than a 2-fold improvement. And CQL is able to solve tasks from various locations, as you can see on the slide. Finally, when our proposed variational information bottleneck regularizer is used to correct for overfitting, and in addition to the early stopping criterion, we find that the performance is increased to 8 out of 9, which is much better than any of the two approaches discussed before. And it can solve the task from locations it could not even previously solve it. This indicates the efficacy of our overfitting correction as well as an early stopping rule in detecting and addressing overfitting. Finally, only for understanding purposes, we evaluate the performance of all policy checkpoints by the learning algorithm to understand the trend in the performance of the policy over the course of training. In this case, we find that when we utilize the variational information bottleneck regularizer, the degradation in the performance with more training steps is usually very mild. Unlike the base CQL algorithm, whose performance drops from 7 out of 9 at the peak Q value point, which is shown in the orange dashed line, to 3 out of 9 as we train more and more, utilizing the variational information bottleneck regularizer stabilizes the performance of CQL over the course of training, and the performance only drops from 8 out of 9 to 7 out of 9. And this indicates the efficacy of our proposed regularizer in stabilizing the learning procedure. Finally, we remark that we also validate our workflow in a number of simulated domains, which require grasping an object from a block drawer or pick and place tasks in simulation, and we discuss this in section 6 of the paper. Thank you.